Here's another example of double counting. The trinomial revision formula for non-negative integers. Here's what it says. Let n, a, and b be in n. Then n choose a times a choose b is n choose b times n minus b, a minus b. Choose n minus b, choose a minus b. So why is it called trinomial revision? Well, these products are called trinomial coefficients, but this is a bit irrelevant right now. Why is it called revision? Because it can be used to revise a product of two binomial coefficients as a different product. That's actually pretty handy when you're working with binomial coefficients. Whenever you see a product of two binomial coefficients where the thing at the bottom of one is at the top of the other, you should actually think of using this formula, perhaps. If you've been paying attention to the solutions of the homework problems, we've actually used particular cases of this a couple times. We have used this long ago, and I think in the case when a and b are less or equal to n, or a is less or equal to b, something like that. So how do we prove this by double counting? Consider the following counting problem. Assume you have n people. How many ways are there to choose a committee consisting of A of this n people, and also choose a subcommittee consisting of B of the A people from the committee? So pictorially, here is how it will look like. You have this set of n people. That's the big square, the yellow one. That's already chosen. You don't get to choose them. You have to choose this green circle, this green oval, the committee, and its subcommittee. So let's get rid of the unnecessary anthropomorphism. Let's just rename everything as sets. So here is, in other words, fix an n-element set capital N. This is our n people. If we want to count all pairs A, B, where B is a subset of A is a subset of N, and B has B elements, and A has A elements. So N are our N people, A is the committee, B is the subcommittee, and we have to choose both A and B. Okay, this is a counting problem. Let's solve it in two ways. Ideally, in one way getting this, and in the other way getting this. So here is the first way to solve it. And before I do anything, let me give these pairs a name. We call such pairs CS pairs for committee, subcommittee pairs. I have to abbreviate it because there is no way I'm not going to misspell committee at some point if I don't. So here is, how would you get this product? Well, it's a product, so you would expect to use the product rule or the dependent product rule. So here is a way to choose a CS pair AB. First, choose A, that is this committee. This can be done in how many ways? And choose A, because N has N elements and A should be having A elements. The way I've labeled the sets, every capital letter, the size of every capital letter should be the corresponding lowercase letter. So A has to be an N element. So A should be an A element set of the fixed N element set capital N. And then choose B. There are A choose B choices for this, since B should be a B element set of the A element set A. And at this point, A is already fixed because we've chosen it in the previous step. Thus, the total number of choices is N choose A times A choose B. Hence, the number of CS pairs is this product. That was the first way. How do we do this? How do we now get this answer? Obviously, n choose b is the number of ways to choose b. So it looks like we should be doing the same thing, except we start by b with b, not with a. So let's choose the subcommittee first, and then choose the committee around it. So here is another way to choose a CS pair AB. This time we go inside out. We begin with B. Choose B. There are n choose B choices for this, since B should be a B element set of the n element set n. Then choose A. And this is complicated because A is no longer just a general subset of n. It has to be a subset that contains B. So it has to be sandwiched between B and n. How do we do this? So how many choices do we have here? A needs to satisfy B subset A subset n. Thus, the B elements of B must be contained in A. So since B is a subset of A. Hence, we only need to choose the remaining A minus B elements of A. So B elements are already accounted for, and we need to choose A elements, so A minus B remain. And this A minus B elements need to come from n without B. Because we've already chosen all the elements of B, we now only have the elements of n without B left to choose from. So choosing A is tantamount to choosing an A minus B element subset of n without B. Because we're really choosing not A anymore, but A without B. But this can be done in n minus b choose n minus b many ways. Why? Well, n without b is an n minus b element set, because b was a b element set. And from this n minus b element set, we need to choose an a minus b element subset. So we use this old formula for how many ways there are to choose a subset, and we get n minus b choose a minus b. So we have this many choices. So the total number of choices by the dependent product principle is this times this. Hence, the number of CS pairs is this product times this product. Sorry, this product. And comparing the two answers, we get n choose A times A choose B equals this here. So because of this proof, this equality is also known as the committee subcommittee. There I already misspelled it. The committee subcommittee identity. And once again, we've proved it only for non-negative integers, which is why I write this here, but it can actually be generalized, and we're going to do this soon. That's in fact what we're going to do next.